Have you ever wondered what really happens when a metal like sodium meets a non-metal like chlorine? Well, it's a classic case of give and take. Sodium loves to give away its outermost electron, while chlorine is more than happy to take it. This transfer of electrons creates charged particles, ions. Sodium becomes positively charged and chlorine becomes negatively charged. These oppositely charged ions attract one another and form a strong bond. This type of bond is called an electrovalent or ionic bond, and it's the foundation of how metals and nonmetals react. Let's look deeper. Take sodium and chlorine. Sodium has one electron in its outermost shell. It gives that electron to chlorine, which needs one to complete its octet. As a result, sodium becomes a Na plus ion and chlorine becomes ACl ion. These two ions now stick together through strong electrostatic forces and form sodium chloride or common salt. Similarly, magnesium donates two electrons, one to each chlorine atom, forming MgCl-2. The bond formed is strong, directional, and based on charge, making the resulting compounds hard and crystalline. But why do atoms behave this way? The answer lies in stability. Atoms want to achieve the electronic configuration of noble gases which have full outermost shells. Metals like magnesium, which have two electrons in their outer shell, lose them to become stable. Their configuration shifts from 2A to 2A, which is the stable shell configuration. Nonmetals like chlorine have 7 electrons in their outer shell. By gaining just one electron, they too reach stability. This push toward achieving noble gas configuration is the driving force behind ionic bonding. So, what's special about the compounds they form? Ionic compounds are usually hard and form regular, repeating crystal structures. They have high melting and boiling points because it takes a lot of energy to break the ionic bonds. In solid state, the ions are locked in place so they don't conduct electricity. But when you melt them or dissolve them in water, the ions become free to move, and that's when they conduct electricity. That's why salt water is a conductor, but a crystal of salt is not. You've already seen sodium chloride, but there are many more examples. Magnesium chloride is found in bath salts. Calcium oxide is used in cement and construction. Potassium iodide is used in medicines. All of them are formed when metals donate electrons and nonmetals accept them. Their predictability and stability make ionic compounds useful across chemistry, biology, and industry. And no matter where you find them, in a lab or a salt shaker, they all share that same electron transfer story. Let's wrap it up. When metals react with nonmetals, they form ionic bonds through the transfer of electrons. Metals lose electrons and become positive ions. Nonmetals gain electrons and become negative ions. These ions attract each other and form strong, stable bonds called electrovalent or ionic bonds. The resulting compounds are solid, have high melting points, and conduct electricity in solution. And the entire process is nature's way of helping atoms reach that sweet spot, the noble gas configuration.